Alright, in this video we'll talk about Newton's laws of motion. So there's three laws and we'll kind of just run through them in order with an example. So let's say we're in outer space. Here I am in outer space. Here's my little space helmet. Okay, so let's say I push a velociraptor, right? So there's a velociraptor near me. I'm like, oh my god, that's scary. Get the velociraptor away from me. Velociraptor's angry. Oh my god. This is a bad velociraptor here. Okay, here's the arm. Okay. So I push the velociraptor. Pew. Push it this way. What should we expect should happen to the velociraptor, right? Well, we're in outer space. So what actually should happen is the velociraptor will keep moving at whatever speed it got to from me pushing it forever in a straight line. So in like a million years, unless there's like other stuff around. Say we're like really far away from everything. It should still be plodding along. Velociraptor, velociraptor, velociraptor. Not speeding up, not slowing down, not changing direction. And this is Newton's first law. A body in uniform motion, the velociraptor, remains in uniform motion, and a body at rest remains at rest, unless acted on by a non-zero net force. So what does that mean? That means that the velociraptor will keep going straight at its constant velocity, right? Unless something else happens to it, unless there's another force. This is also saying that, say I'm still. So here's me, and say I'm just chilling, and I'm still. I'm going to stay still. I'm going to remain at rest, unless I get acted on by a non-zero net force. So then if a velociraptor came and pushed me, I would be in the same fate. I would just be moving, forever and ever and ever, unless another force came by, right? So let's say that our velociraptor, well, let's say someone put a wall in outer space, right? The velociraptor's moving, boom, it would hit the wall. What would happen? It would probably bounce back and slow down, right? What happened? Well, it stopped moving in uniform motion, right? It's now accelerated, it's changed directions. But the only reason it did that is because some other force came, right? The force from hitting the wall. Okay, so that's Newton's first law of motion. And it's kind of weird and non-intuitive for us because we very rarely get circumstances where stuff like that happens. And the main reason for that is because of friction and air resistance. So suppose I'm not in outer space anymore. Uh-oh, I can't draw. Mr. U can't draw. Hey yo. And he's riding a bike. Okay, Mr. U's riding a bike. Here we go, my bike. And say I start pedaling for a little bit, so I've built up some speed, and I just stop. Now, according to Newton's first law, we would expect that I would just keep going in a straight line forever and ever, unless some other force acted on me, right? And we know that from experience, what will happen is I'll kind of be going, and I'll slow down, slow down, eventually I'll stop, right? Why do I stop? Well, there's friction, right? The friction between my tires on the road and the air resistance blowing in my hair, right? That's all forces. Those are all non-zero net forces that are making me accelerate. What are they making me do? They're making me slow down. So it's very rare that we're in a circumstance where there are no non-zero net forces, kind of really only in the far reaches of outer space, hence the velociraptor and I. Yay. Okay, Newton's second law just says that acceleration of an object acted on by a force, so say the acceleration of the velociraptor that I push, is proportional to the magnitude of the force, that's just how strong the force is, and inversely proportional to the mass of the object. What that means is really simple. It means that for me to get the velociraptor to move faster, I've got to push it harder, right? Stronger force, easy. The second thing is that the more massive this velociraptor is, right? If it's a baby velociraptor, ooh, I'm a baby velociraptor. This is what baby velociraptors look like. If it's a baby velociraptor, I don't have to push it as hard. I don't know why it looks like this, okay? I don't have to push it as hard if it has smaller mass, right? The more mass it has, the stronger force you need to get it to have the same acceleration. Again, that's kind of intuitive to us. And we can explain that in an equation. Force equals mass times acceleration. So if you want it to have a high acceleration, you have to have a high force. If it has a high mass, you have to have a high force. Newton's third law is that if object A, say that's me, exerts a force on object B, say that's the velociraptor, object B exerts an opposite but equal force on object A. That means when I push the velociraptor this way, we kind of know this from experience, there'll be a force that pushes me this way. So then I'll float backwards forever and ever and ever. And that's Newton's three laws of motion.